My name is Pratik Patel. I lead the developer relations team at Azul Systems. How many people have heard of Azul before? Oh, that's not a lot. Okay. So I also lead the Atlanta Jug, and out of that, we do a nice conference called DevNexus, which is in the spring in Atlanta. But the most important thing on here is my Twitter handle. So if you have any questions after this session, please email me or send me a note on Twitter. And I do work for Azul Systems, and we actually have a really nice OpenJDK build that's free called Azul Zulu that gets about 200 million downloads a year. A lot of people use it. It's completely free. And then we have a high-performance Java virtual machine called Azul Platform Prime, which I'll talk about a little bit at the end of this, which has its own garbage collector called C4. But this specific session, well, before we get into that, again, Azul has a free garbage collector, a free OpenJDK build that lots of people use. Is completely free and will be free forever. And then our high-performance JVM is a drop-in replacement for any OpenJDK-based Java virtual machine. And with no code changes, for example, with Apache Kafka, you can see 40% improvement in performance. And lots of other different apps can get performance improvement, again, just by replacing the JVM with that. Okay. So let's start with a few questions. What's the best GC for running Java workloads on the cloud? Anyone want to take a guess? I know it's hard to hear, but just shout it out. Anybody? No? Okay, so the answer to this question, this is a trick question, okay? The answer is it depends on your application, right? Because as a software developer and as a software architect, whatever you might do, you understand that software engineering is a series of trade-offs, right? If you have something that is, for example, for this session, a better garbage collector for certain scenarios, the trade-off that you make might be in more memory or more CPU usage and things like that. So we'll talk about that a little bit so that you can understand what some of the trade-offs are between some of the different garbage collectors. Now, is everyone in this room a Java developer? Who's not a Java developer? You're not Java developers. What do you develop in? What's that? Okay, why are you in this session? I'm just kidding. I'm just kidding. All right, so this is heavily based on Java, but if you look at other platforms, for example, C# that have garbage collection or basically a VM-based language, they have similar strategies for doing this thing. So hopefully you'll get something out of it, right? The real answer to this question, though, what's the best GC for running Java workloads on the cloud, is does it really matter which garbage collector you use, okay? So this is what I'd like for you to think about as we're going through this. Think of your application and what your application does, what your app profile does, how you run it. Do you run it on-prem? Do you run it in a CPU-constrained environment like the cloud, et cetera? So be thinking about that as we look at these different garbage collectors. They'll give you a better idea of what is a good garbage collector. All right, so what we're going to do in this session in the next 45 minutes is we're going to do a quick review of garbage collection algorithms, and then we're going to talk about garbage collection and performance, and then talk about different scenarios as we go along in terms of what is a good garbage collector for this kind of scenario versus this other one, okay? Now, is anyone in here deeply familiar with how garbage collection works? So I know how fast to go through this first part. Okay, so a few people, good. So I'll spend a little bit of time talking about GC algorithms and how garbage collection works and things like that to give you a better idea of like what it means when we're talking about generational garbage collection, stop the world, and other things like that. Okay, so why do we need a garbage collector? So Java is a VM-based language or a virtual machine-based language. There are other languages also based on VMs. For example, C# is one of those, Python, as well as JavaScript, right? So Java and JavaScript are the same language because the first 4 letters are the same, right? I'm just joking, of course. But get the idea. So what we do with a VM-based language, what it does is it tracks the memory for you, and because it's tracking the memory for you and you're not doing it by hand, for example, with something like C or C++, it's actually more efficient than coding it by hand in some ways, okay? Now, this is a little bit of, it depends on how you code apps and stuff like that, but the main thing is the second bullet on this slide, which is that you don't need to do manual memory management, which is the key, because as developers, you don't want to spend a lot of time doing that kind of stuff, right? Now, in terms of the way the memory is split up into the VM, there are a couple of different things. There's the stack, there's the heap, and then the heap is the larger part of the memory, right? Hopefully everyone knows what the stack is, that whenever you execute a method and then that executes another method, it has something called a stack, which it puts things on. So as the stack grows and you do execution, you pop things off the stack, but that does take some memory, and that, more importantly, that will keep a handle to references in memory. So the bigger your stack is, the more memory you'll use concurrently at that point in time. Now, the heap is the larger part of memory where objects are stored that you're working on, and the heap is split into parts. Okay, and this is what the JVM heap looks like. You have young, tenured, and permanent. So these are the three major parts of the heap. And within the young, you have Eden, Survivor 0, and Survivor 1. So this is the working memory that the JVM has as it's going and doing things. As you create objects and you do calculations, data processing, whatever, and you don't need those objects anymore, they get typically most of the memory management that happens, you want to happen in the young gen because that's very, very short-lived. So you create an object, you do some stuff with it, and then you release that object, or the JVM releases that object once it figures out that you're no longer using it. Okay? So these are the three major parts, and then the young gen is broken down into three smaller parts. All right? Now, there are different garbage collection types. So as you're using this memory, what happens is at some point in time, the JVM needs to figure out when to release that memory. What happens if you never release memory? This is not a trick question. There are trick questions later. But what happens if you never release memory in your application? You get an out-of-memory error, and your app goes crashing down and stops working, right? So the GC has to go and do that. Now, there are different types of garbage collection types. Minor GCs typically happen in the young gen part of this. So basically, you're doing small amounts of memory management. The JVM is doing small amounts of memory management, i.e. deallocating objects as it doesn't need them. Okay? Now, major garbage collections happen in the last two parts, right? The tenured and the permanent part, where you have a lot of memory that you might be potentially using, and now you need to clear all this memory out, or the JVM decides it needs to clear all this memory out to make space for your application to create more objects. Okay? And the permanent part of it, even though it's called permanent, can also be swept. Now, you might be asking, what is permanent? Permanent sounds like it never changes. But in reality, what happens in the JVM is the permanent part of the VM, which is, for example, where you load classes, right? So when the JVM starts, you have to load all the jar files. The jar files get put into permanent part of the memory here. And typically, you don't have to go and remove anything in the permanent. That's why it's called permanent. But sometimes if you do class unloading, you may want, the JVM may decide it needs to sweep the memory that's in there too to free up permanent space or more space on the heap. Okay? Now, there are also different types of GC algorithms, right? There's stop the world, or what we call STW. Stop the world, what it does is it stops all processing on all threads, so the Java Virtual Machine's garbage collector can go through and mark objects and go and delete them. So when you stop the JVM, zero processing is happening. Basically, the JVM is frozen while some threads go and work to free up memory for processing to continue. And then there's also incremental and monolithic. We'll talk about those two in a little bit more detail in just a second, as well as stop the world. Okay? And then there's also different strategies for garbage collectors. And you'll see these in play as we talk about the different garbage collectors, right? There's parallel and concurrent. And I don't want to talk too much about them. I have some nice diagrams that'll show you what that actually means when your JVM is running. Okay? All right, so let's look at from the last slide, parallel and concurrent. Okay, so you have a GC thread that goes and does something. The one on the far left is single-threaded garbage collection. There's actually a single-threaded garbage collector called the serial garbage collector. And then you also have a parallel garbage collector, and then you can have a concurrent garbage collector. Now, the difference between the second two is you can see that the parallel garbage collector and the one on the left with the single GC thread, those are stop-the-world garbage collectors. That means that all processing stops while the JVM is going and marking marking objects and removing them from memory. The one on the right here, the concurrent garbage collector, it does garbage collection while the JVM is still processing, while it's still doing stuff. Okay? So we'll talk about all three in detail, and we'll show you some examples of those that are running. All right? So in terms of the different phases of garbage collection, there's tracing, freeing, and then sometimes there's also moving. What moving means is if you have some objects which the JVM detects is being used and it's in Survivor 0 or Eden or S1, it will move it into the tenured, basically into a different part of the heap. Okay, so that's what relocation or moving means when we talk about garbage collection and moving memory objects around. Okay, so that was a very quick overview of what garbage collection is. Now let's talk about some of the garbage collectors that are in the JVM. Right, so the first one is the most simplest. It's called the serial garbage collector. Right? It's single-threaded and it's extremely simple, and it is stop the world. So what it does, essentially stops all processing, all threads are paused, so there's no processing going on, and it uses a single thread to go and find objects which can be deallocated and freed up from memory. Okay? And serial garbage collectors are actually useful. It's good when you have, for example, an application running on a single core with a small heap. But more importantly, you don't have any requirements for pause times. So when we use the stop the world garbage collector, it does pause the JVM. Now the question might be, how long does the JVM pause? Well, it depends on how big the heap is and how much memory is being used at that point in time. So if your application can be paused for half a second, 5 seconds, 10 seconds, whatever, and you don't really care about that pause time, then something like a serial garbage collector is good. But again, the use case for a serial garbage collector is when you have a single core, CPU core, single virtual thread that your Java virtual machine is running on, and you have a very small amount of memory. Because you don't want to have a very large amount of pause, because again, everything is paused and there's no processing happen. Okay, so again, for single-threaded apps, serial garbage collectors are good. For development environments where you might be running on your laptop, you don't have a lot of memory, you're just doing some testing or development, that's also good. But specifically for cloud scenarios, if you have a microservice running on a very small node, again, small amount of memory and a single core or a single virtual thread, that's when this specific garbage collector can be good. Okay, and again, this is what it looks like. You have application threads. When the garbage collector kicks in, all processing stops. It goes and marks objects and removes the objects it can, and then when it's done doing that, after it's done doing that, basically after the pause, application threads continue running and your app starts working again. All right, so let's look at parallel garbage collectors. As you can imagine, parallel garbage collectors are multi-threaded, but this is also a relatively simple garbage collection algorithm. Okay? So this is specifically good for multi-core systems where you have a small amount of heap. So you have more than one CPU or more than one virtual CPU, you have a small heap, and again, you don't really care about pauses that much. You care about really long pauses, but not like small pauses. But this is good when you need the maximum amount of performance, because the garbage collector can spin up multiple threads, look at objects using multiple threads, and go and remove objects more quickly because it's multi-threaded, okay? And again, for peak performance and with no pause time requirements. Right, so what are some scenarios that this is specifically good for? If you're doing batch processing, some kind of very large data processing where you have to work with a lot of objects, you create a lot of objects and then you need to destroy them after you've done the processing. These are 3 scenarios where a parallel garbage collector is good. Again, the key premise here is you need peak performance for your garbage collector, right? You need peak performance for your application. Okay? And again, this looks something like this. Right? You have application threads, you have multiple threads doing garbage collection, so it's faster to do that garbage collection, and then the pause time is smaller because you have multiple threads working, doing garbage collection. Okay? Now again, you need to have multiple cores. The more cores you have, the more threads the garbage collector can spin up to do that garbage collection. Okay? All right, so the next category we want to talk about is concurrent mark and sweep, all right, otherwise known as CMS. So what this does is, while the application is actually running, there are threads in the garbage collector which are going and looking for objects to remove. It doesn't actually remove those objects while the app is running. That's the final one that we're going to look at. But we concurrently sweeping while the app is still running. Right? The scenario that this is good for is when response time is more important than throughput. Right? So we have the parallel is good for throughput when you need to do a lot of processing very quickly and you're able to tolerate a larger pause time in the garbage collector. The CMS garbage collector will give you a low pause time, typically less than 1 second, and what you care about in your application is the response time that the application gets. Right? So as we shrink the amount of time that the garbage collector pauses, the user that's on the other side of this, right, using your application, will see a less pause time so they get a better user experience. Okay? All right, so what are some cases where this is good for? So your standard web application. So how many people build with Spring Boot, for example? Okay, right, so that's probably everyone in here. So if you're using a Spring Boot application, you typically go on and use a CMS, and not surprisingly, the default garbage collector that you have in the JVM is a CMS-based garbage collector. So if you're thinking that, oh, I've never changed the garbage collector and I write a Spring Boot application, doesn't matter because you already have a CMS garbage collector. Because typically, when you deploy something like a Spring Boot application, you have multiple cores and you have multiple CPUs and a good amount of memory to run with, right? Similarly, with REST API backends, and also, again, this is key in terms of sizing, you have a medium-sized application that uses a medium amount of memory. So what does medium amount of memory mean in this case? A medium amount of memory would be something like 2 gigs of RAM, 4, 8, 16, maybe even 32 or 64. But typically, when I work with customers and they go beyond 64 gigs of RAM, you're starting to get into a point where the garbage collecting time will get longer than 1 second, right? Because the larger your heap is, the more time it takes to go and do garbage collection, the more overhead it adds, the more CPU you need to do it concurrently, et cetera, et cetera. Okay? So let's see what this looks like in a diagram. Right? So as you can see here, let's see if this works, right. So you can see here, this thread right here is doing marking of objects which may not be being used while the stop the world initial marking and remarking, basically checking that objects do actually need to be removed, will stop the world, but it stops it for a small amount of time. Okay? And when we get to the sweep phase right here, you can see that we do some marking and we can also get rid of objects while the application is running. Okay? So the blue lines here are the app is running or application threads which are running. And then the orange lines are when the garbage collector is doing either marking or sweeping of objects in memory. All right? So let's talk about G1GC, which is the default garbage collector currently in Java. So this is good for medium to large heaps, but it does require a moderate amount of CPU utilization. So when we think about moderate amounts of CPU utilization, what this means is that you need to have more CPU cores available so that the garbage collector can use those CPU threads or cores to be able to do its work. Okay? So if you use something like G1GC and you only have 2 threads, it's not going to work well. It may not work at all, actually. So you have to be careful about this. You have to give it at least, I would say, a minimum of 4 CPU threads. 8 or 16 is better for something like this. Okay? And again, the use case for this is when response time is more important than throughput. So if you have a user at the other end, you have a web application, and you want them to get a response within less than a second, within less than 5 seconds, this is when G1GC is good for something like this. Okay? So again, this is the default garbage collector that is in the VM currently. This is typically good for low workloads. Testing, 1, 2, 3. Okay, are we back? Testing, 1, 2, 3. Testing, 1, 2, okay. Oh, testing. Testing, 1, 2, 3. Testing, 1, 2, 3. Testing, 1. You want to use this for now? Okay. All right, I have to get behind the microphone for the time being. Testing, 1, 2, 3. All right, I'll just stand here and use this. Okay. I don't like to stand behind the podium, but all right. So G1 is good when you have large applications, but it's not good for small applications because you have more threads. You need to have more threads, right? A small application will typically have a few cores, which is not enough to support the garbage collector. And the response, it's responsive with medium to large heaps. So again, mixed workloads, different types of scenarios. So if we look at this from a diagram point of view, we have, Let's put this up. Okay. So we still have a very small the world. Testing, 1, 2, 3. Is that good? All right. I guess we'll do this for now. All right. So again, we have a very small amount of pause time for doing Stop the World, where we do young generation initial marking. But you can see that we have application threads which are running concurrently while we're doing scanning and marking and removing of objects, right? So you can see here's the remarking. We do some cleanup. We may do some copying from young gen into old gen, et cetera, in this case. Okay. Again, this is G1 GC, good for large applications, but not good for small applications. All right, so how many people have heard of Shenandoah, which is a newer garbage collector in the VM? Okay, do you actually use it in production? Do you use it in production? Oh, you do? A little bit, okay. Do you use it in production? No, okay. All right, so Shenandoah is what's called a generational garbage collector. So let's have a look at that. I'm sorry, it's a non-generational. We'll talk about some which are generational in a minute. So Shenandoah is good specifically for low latency and high throughput environments or workloads. Now, some of the other ones that we've looked at so far, I've said, oh, it's good for low latency, but not good for high throughput. So how is something like this garbage collector good for both low latency and high throughput? The trade-off that you're making in this case is that you need more CPU threads and you need more memory for the garbage collector to be able to manage the memory. So the trade-off you're making is that you get low latency and high throughput, but you have to use more resources for this, okay? Now the problem with doing this is that, I mean, this sounds great, right? It's like low throughput, low latency and high throughput. Trade-off is more CPU and more memory. The problem there becomes is now you have to have a much larger server to be able to support this garbage collector style. And typically, when you have more CPU cores, especially in the cloud, more CPU cores and more memory, what does that mean? It means you have to spend more money to be able to do that, right? Because if you get something, for example, on AWS, which is, let's say, 8 cores and 16 gigs of RAM, it may cost you $100 a month. I'm just making those numbers up to give you an idea of scale. For something like this, you typically would need to double the amount of CPU cores and double the amount of memory that you're using. So now instead of spending $100 a month to run this application, you're spending $200 a month or something like that, okay? So the trade-off is you need more CPU cores, you need more memory, but you have to pay more to be able to run it, okay? As a software engineer, you know that when you deploy anything into production, nothing is free. Everything costs money, right? And time sometimes. So again, this is good for when response time is key and when you need to have a very large heap, okay? Now, what does it mean by very large heap? Now we're talking about 256 gigs of memory or heap that you need, or more, 256 gigs, half a terabyte or a terabyte of heap. And now, let me ask a question. For your applications that you deploy in production, how many people use, let's start with 16 gigs of RAM, okay? That's pretty typical. And you probably build Spring Boot applications for those applications. No? Something else? What kind of app is it? Okay, gotcha. All right. Now, how many people deploy with 32 gigs of RAM? Okay. 64? Okay. 128? Okay. 256? Anyone with more than 256 gigs of RAM? Okay. Wow. How big is your heap? Like a terabyte? Yeah, huge. What's that? Half a terabyte. So nobody deploys anything with more than half a terabyte. How big is your heap? 2 terabytes. Okay. Which garbage collector do you use? You use Shenandoah. Okay, there you go. It makes sense. We'll talk about some other ones that you might be interested in a few minutes. But the problem with those large heaps is you have to watch out for pause times because obviously trying to garbage collect a half a terabyte of RAM can pause your application if you use one of the other garbage collectors, not for seconds, but for minutes. I was working with a customer recently where their garbage collection time was 15 minutes. Literally, the app would stop for 15 minutes. And we're like, why are you using a standard G1, GC, or parallel garbage collector? But anyways, we can talk about that later over beer. Okay. So again, Shenandoah, when to use, you have a large application, you need a responsive app with a medium to large heap, and you potentially have a mixed workload that you're throwing at it. When I say mixed workload here, that means it's a standard web application, plus you're doing heavy data processing. Maybe you're doing some kind of batch processing, which is very object creation heavy or something like that, okay? All right, so let's talk about one of the newer garbage collectors, which is called ZGC or ZGC, depending on how you want to pronounce it. So ZGC is good for a very low latency and very high throughput environment, okay? But again, the trade-off here is that you have to have much more CPU to be able to support ZGC, right? So with Shenandoah, you probably need a minimum of like 32 cores or 64 threads to be able to do it, right? How many threads do you run Shenandoah with? What's that? Oh, you don't know, right? It's probably, you probably have, I would say, a minimum of 32 cores, which would be approximately 64 virtual threads or 128 virtual threads. So that's a lot of horsepower to be able to support this. So because of the higher CPU utilization, you do need to have a large amount of CPU. Of course, you're going to have a large amount of memory, okay? So again, ZGC is good when you have when response time is high priority. The user needs to get a response within 100 milliseconds, maybe at most 250 milliseconds or less. And again, you have a very large heap, over 100 gigabytes, let's say over 100 gigabytes at least for something like this. Okay, so low latency apps, large scale systems. Now, ZGC is only available on newer JVMs. So JDK 15, or ideally 21 plus. Actually, I haven't asked this question before. Let's start from the top. How many people are deploying apps with Java 22? 22, anybody? That just came out in March, right? Just making sure I'm not crazy. That came out in March, right? Yeah, I did. How about Java 21? Okay, that's cool. That's about a third of people. Java 17? Okay, it's pretty much everybody. How about Java 11? Okay, a few people on Java 11. Okay, now try to be honest for these next ones. How many people are deploying with Java 8 still in production? Okay, that's okay. That's fine. Java 7? No? Java 6? Anybody? Anyone still stuck in 2005? I'm just kidding. Okay, so that's good to know. So at Azul, we actually support all the way down to Java 6 because you would be surprised the number of people that are still running really old versions of the JVM, right? But like everyone in this room, most people are on at least Java 11 and above, which is nice. Okay, so the final one I want to talk about, this is a proprietary garbage collector that is only in Azul's high-performance Java virtual machine called C4. Now, one of the differences between C4 and ZGC, they're both similar garbage collectors, and we'll talk about it in just a second, but that should say C4 in it. So it's good for very large heaps. So we have customers running 2 terabytes, 4 terabytes of RAM or heap in their JVM. But the nice thing is that instead of having high CPU utilization, it has a moderate amount of CPU utilization. Again, this is a proprietary garbage collector. It's good for when response time is a key. You need very good response time. And again, you're running a very, very large heap. Okay? Now, it's good for low latency, sensitive applications. It's also good for very large or large to very large applications, but it is not good for small applications because of the amount of overhead that's required. You do need, like ZGC, you do need a large number of CPU cores to be able to support the garbage collector, and the garbage collector specifically working concurrently, okay? So again, it's responsive with very large heaps. We actually have customers that come to us who are running other garbage collectors, and they can't do anything because it's an old application or the app has very sensitive low latency requirements, and they come to us and they drop this specific Java virtual machine in Azul Platform Prime, and they use the C4 garbage collector to be able to keep running the application, and it can keep growing and things like that. Okay, so let's do a quick recap of the different garbage collectors here. All right, so this is the chart, and a lot of these diagrams are actually not mine. They're from my colleague Garrett Grunwald, who has a similar talk, but where he dives deeper into the different garbage collectors. Okay, so let's have a quick look at this to give you an idea of everything that we've talked about so far. Okay, so on the left, you can see that we have the different categories of things that you might be interested in or that you care about. And on the top, you have all the, why is this not working? There it is. And on the top here, you have all of the different types of garbage collectors that we've talked about so far. Actually, the one that we haven't talked about is the one in the middle called Epsilon, which is a single-threaded, basically it's no garbage collection. So this is good when you have a really, really low memory environment, something like a Raspberry Pi that you want to run a Java application on, okay? It's not really good for production use aside from like IoT devices and things like that, okay? But if we look at this diagram, I mean, you can see that we have our serial one here. It's not parallel, it's not concurrent, it is generational, it's good for these types of heaps. It will have longer pause times, low throughput, et cetera, but you can see that the trade-off you're making here is that you have a low amount of CPU overhead, which means you don't have to have a lot of CPU cycles, or sorry, a lot of CPU threads to be able to run this. You can run this in a constrained environment or basically in a server with the 1 or 2 cores. Okay, you can see parallel JDK or parallel garbage collectors here. It's parallel and gives you get moderate pause times with it. The throughput is high, but you get low latency, higher performance, but you get lower CPU requirements than the other ones. And then if we move on to CMS, G1, GC, et cetera, you can get a better idea of all the different types of environments that you can run this stuff in. Now, the other thing to note is a lot of these garbage collectors are only available in certain versions of the JVM. So for example, Shenandoah came out in JDK 11, so you have to be running that, at least minimally for that. For this one right here, which is ZGC, they initially introduced ZGC in JDK 15, but it was non-generational, which means that it was a little bit slower and required a little bit more CPU and had more pause times in terms of the, where's the latency right here, right? So you can see the latency, low latency, and high throughput, okay? And of course, the best garbage collector for large heaps and for high throughput environments is C4. That garbage collector has been around for probably like the last 12 years or something. But again, one of the key differences between the ZGC, which is currently available, and Azul Prime is that the garbage collector has been developed over a much longer amount of time, and both support large heaps. And you can see that in this category right here, the no yes means that in JDK 15, it was not generational, but in JDK 21 plus, it is generational. But ZGC is a much newer garbage collector. All right, so that's actually the end of this presentation. I usually leave more time for questions and stuff, and usually I take questions during the presentation, but it's a little bit more difficult to take questions in this specific room. So anyone have any comments or questions on this specific, well, we'll go back to this diagram. Any comments or questions so far? Okay. No comments or questions? Okay, well, I'll be up here for a bit, so if you want to talk specifically about your use case scenario and which garbage collector you're using, or if you're having a problem, I've worked with literally hundreds of customers on helping them tune garbage collectors and also pick a garbage collector, so I'm happy to talk to you about that and see if there's some pointers I can give you. Thank you for coming to the presentation. I hope you enjoyed it.